Hey everyone, welcome back to another Calculus 1 video. Today we have two very special rules to talk about, the product rule and the quotient rule. These two rules give us a way of not only doing problems we already know how to do much faster, but also doing problems we have no way of doing before the existence of these two very special rules. So before we go on, let's state what they are. Let f and g be some functions of x. Number one here is going to be my product rule. The derivative of the product of f and g, f times g. Turns out that's always going to be fg prime plus gf prime. So you do a little bit of mixing and matching with normals and derivatives. Fg prime plus gf prime. Number two is our quotient rule. He's going to look a little more nasty, look a little more prickly, but he goes like this. Gf prime minus fg prime, all divided by plain old g squared. Again, product rule and quotient rule, and later on in the video I'll show you guys proofs for why these are true. But for now, let's just get a feel for how to use them in computations. Oh, and of course the product rule, the denominator can't be, or quotient rule, the denominator can't be 0. Alright, let's start with the product rule here. How does this work? Well, let's start with something we already know how to do. Let's let this function h be x to the third plus 2x times x squared plus 5x. Find the derivative of that whole thing. Well, one way to do it is to do it the way we already know how. Get rid of those parentheses, just FOIL. So after foiling, let's see, what are we going to get here? I believe that first term will be an x to the 5th. Second one will be a 5x to the 4th. Third a 2x cubed, and finally a 10x squared. And now it's just stuff from last video. Take the derivative of each term since the main operation is addition, and there we have it. But the product rule gives us an alternative way of doing this. And he goes like so. So looking back at our function h, I'll label that first x term f, and that second x term g. So f is x cubed plus 2x, and g is x squared plus 5x, and those give us f prime and g prime up top with a simple power rule application. Now we stick them in our product rule, fg prime plus gf prime, and we get this. By the way, once you reach this point, you can box this answer. If the problem doesn't say simplify, then you are done. But just as a sanity check to make sure it's exactly the same as the derivative we computed on the left, let's go ahead and FOIL out this guy. So we get something like so. Like terms I'm underlining. Another pair of like terms I'm underlining. And final two times. Indeed. So the product rule is in keeping with the way we already know to do things. So you may think, okay, well, what's the point of the product rule? If it's just, if we have a perfectly acceptable rule, why do we need the product rule in addition to that? Well, if we have a function like this, well, for this guy, there's absolutely no way to do techniques we've learned previously. We have to fall back on the product rule. We can't FOIL a cosine. What does that even mean? What does that even mean? So here, I'm labeling my f and my g just like before. F is the first stuff with x, g is the second stuff with x in it, and I differentiate each one. F prime gives me that, g prime gives me a negative sign. Again, remember your trig rules for sine and cosine derivative rules? There they are in pink. And now we plug them into our product rule formula. There he is, fg prime plus gf prime. Again, we mix and match the normals with the derivatives, and doing that gives us this. And once again, we're done. So that is the power of the product rule. And what I'm noting here in green again, the product does not say, this problem doesn't say simplify, so if the problem does not say simplify, you are free to box your answer as soon as you apply the product rule. Alright, I want you to pause the video for a moment or two to try this one. Try this one on for size. Again, this is something you would not be able to do with previous techniques because we have an e to the x and we have a sine of x. Can't really FOIL those. So go ahead and try this guy. Okay, well, again, label your first stuff with x in it, the f function, the second stuff with x in it, the g function, take your derivatives and throw them in your product rule formula. Doing so leaves you with, well, it leaves you with this. Leaves you with this. There we have it. This problem doesn't say simplify, so we're done. I'm just going to box it and walk away. Just box it and walk away. Walk on over to the next problem. But that is the niceness of the product rule. Now then, what about number 2? Rule number 2, the quotient rule. Again, he goes like so. gf prime minus fg prime all over the denominator g squared. That is the derivative of that quotient of functions of x. So here's an example. Something we already know how to do. Here's my h function, find h prime. So 2 ways of doing this. I can break up that one fraction into 3, just like you guys did in one of the worksheets, I believe. So we algebraize them first. We simplify each fraction. There we have it. And then we take the derivative using simple power rule, simple derivative properties. And there it is. 1 minus 4x squared. Now then, the quotient rule gives us another way of looking at this. I'm going to label the top function f, the bottom function g, and once again, just like I did for the product rule, I'm going to compute their derivatives up there in gold, and after computing those derivatives, I throw them in my quotient rule formula. And there he is. 2x plus 2 goes with f prime, 1 goes with g prime, and g, plain old f are given to me, so I get this. And just again, as a sanity check, I'm going to prove to you that this is exactly the same thing as the stuff I boxed in gold, and yes, look at this, it is. You just got to do a bit of algebra, but the quotient rule result perfectly matches the normal algebra result on the left. So there's a little sanity check just to ensure you that this is a true statement. This is a true statement. But now, just like I did for the product rule, let's see a formula, let's see a function that we have no hope of doing until we met our friend the quotient rule. Again, I can't break this up into 2 fractions because there's more than one thing in the denominator. But the quotient rule sweeps in to save the day. I compute f prime, I compute g prime, I toss them right on into my quotient rule formula, like so, and it's business as usual. And there we have it. Once again, the problem doesn't say simplify, so I'm just going to go ahead and box my answer and move on to the next problem. The next problemo. Well, I want you guys to notice something. If I call the top the high function and the bottom the low function, here's an easy way to remember the quotient rule formula. Low d high minus high d low over low squared. So low times the derivative of the high minus high times the derivative of the low over low squared. By the way, in the formal mathematical literature, this rule, the quotient rule, is sometimes called the Adam Sandler rule. It's a real thing. It's a real thing in formal math because if you say this in an Adam Sandler accent, it really sticks. It really sticks. So, low d high minus high d low over low squared. So you get the idea. Try it on your own. It's a lot of fun, and it'll stick with you. So try this, guys. Try it. Try this problem on your own. Low d high, high d low over low squared, that bad boy. Okay, well, now that you've had a minute to take a stab or two, low d high minus high d low, all over low squared, and voila, ladies and gents, we are done. We're done. Ain't that a beaut? I think so. But once more, why are the product rule and the quotient rule always true? Is this just magic I'm doing? Absolutely not. There is a reason. So it's proof time. Proof time is upon us. Got to start with the product rule. It's actually a bit easier than the quotient rule proof. And here we go. I am going to fall back on my limit definition of the derivative. You always have to do that for proofs for derivative formulas. As you've seen so far with the power rule and the product and the properties we showed in the previous video. Always have to do your product rule. Or your, what am I saying? Limit definition of the derivative. So that's what I'm doing here. And I'm going to do something weird. I'm going to add a random 0 into my numerator. Or is it random? I'm going to rewrite that 0 in a very clever way. I'm going to rewrite it as negative f of x, g of x plus h, plus f of x, g of x plus h. Again, if you add those two things, you get 0. So I'm going to throw that weird way of writing 0 into my numerator of my limit rule, my limit definition. Upon doing that, I'm going to break this big fraction up into 2 fractions of equal size. First fraction gets a green part. The second fraction gets the other green part, like so. There we have it. And then I'm going to use limit properties to distribute that limit as h goes to 0 to both fractions. I'm allowed to do that. And then, notice, g of x plus h and g of x plus h are in common to the first fraction. F of x and f of x is common to the second. So I'm going to pull them out. I'm going to factor them out of my fractions like so. G of x plus h from the first one and f of x from the second one. So there we go. Now notice what fractions we're left with. Those look awfully familiar. They look like limit definition-y things of the derivatives of f and g, and let's see what happens. Once again, I'm going to distribute my limit to both fractions from the first pair of terms and both terms in the second pair. So I have 4 limits overall. Let's compute all 4 of these limits. Start with the easy one. Let's start with that first one. As h goes to 0, g of x plus h becomes g of x plus 0, or just g of x. And then that second guy in gold, look, there's no h term in that f of x, so as h approaches 0, f of x is just f of x. F of x is a constant as far as h is concerned. And finally, these 2 guys in blue, these are the definitions. The very definitions of f prime and g prime, respectively. And there is our product rule, gf prime plus fg prime. And voila, we're done. It's just applying the limit definition of the derivative with a little bit of weird algebra thrown in. But it's a pretty amazing result. It's unexpected for sure. You wouldn't think to rewrite 0 in that way, but... Alright, now when, suppose I'm doing a noir scheme here, black and white. How about we tackle the harder one? How about we tackle the quotient rule? Again, applying limit definition of the derivative. That's what you always have to do in proofs of derivative formulas and properties. I get f of x plus h over g of x plus h minus f of x over g of x all over h. So, ooh, I got some fractions within fractions. And within fractions, first let me get rid of the big fraction. Let me just multiply everything by 1 over h over 1 over h. So I get the limit as h approaches 0 of 1 over h all times that numerator. But again, I don't much like that numerator the way it is now. I'm going to make him one fraction, and I can do it so by getting an LCD. And here's the LCD. It's going to be g of x times g of x plus h. So, fancy way of subtracting fractions gives us this. F of x plus h times g of x minus f of x times g of x plus h all over g times g of x plus h. Why did I do that? Well, once again, I am going to throw in what would seem like a very random 0, here this time in red. A very random 0, but just like the product rule proof, I will rewrite that guy in the most useful way possible for this proof. And he shall be rewritten like so. Minus f of x times g of x plus f of x times g of x. That is 0, as you can see. So no change except to that 0. I've just rewritten it. And again. Well, before the again, how about we break up that one huge fraction, the huge fraction, into 2. I'm gonna g of x and g of x plus h. I'm gonna pull them out into a separate fraction. And I'm going to put the h back in the denominator of that first big fraction. So just multiplying that first fraction by 1 over h. Voila, there he is, back where he was. And as you can guess, that first big fraction, which I will illustrate up here at the very top, I'm going to break up that one big fraction into 2. The first little fraction is going to get that first red piece. The second fraction is going to get that second red piece. And that last term with the g and the g of x plus h, I'm going to ignore him for now. He'll become important at the very end. But for now, I want to pay attention to that first bracketed term. What's constant to that first fraction? Well, well, common and constant is the g of x, First, what I'm showing here is I can just put the limit to each of those three terms. But again, going back to the question of what's common? What's common to that first fraction? Well, before addressing commonality, notice that this guy that I'm boxing here in blue, I can rewrite as minus. Can you factor out a -1 to rewrite him like so? So I'm going to replace him with that negative parentheses f of x times g of x plus h minus f of x times g of x. Okay, now finally, back to the question of commonality. I'm going to, first I'll factor out the -1. Notice that first fraction, there's a g of x and a g of x common to the numerator. In the second one, there's an f of x and an f of x common to the numerator. So I can yank them out front. I can just factor them out. I can factor them out like so. Just algebra. It's nothing other than algebra, with admittedly nasty looking terms, but they can grow on you. They're quite pretty in their own way. Well, again, we are taking the limit again with respect to h. So anything that doesn't have an h is, for all intents and purposes, it's a constant. There is no h in either g or f. They are constants in this limit problem, so I am going to pull them right on out of my limit. So I not only factor the g and the f of x, I can pull them out of the limit problem entirely, and I am left with this. We have what looks to be, we could be wrong, but I don't think we are. What these look to be the very definitions of g prime and f prime for these first two limits. And that second limit with the g, I'm going to take that limit and put it in the bottom. So we have 4 limits to compute. 4 limits to compute. And let's see if it matches our quotient rule formula. Let's start with the first one. This, again, is the very definition of f prime, that second guy in violet. Light violet is the definition of g prime, the very definition, just the limit definition of the derivative for both of those. There we have it. And now, these last two, as h approaches 0, g of x, that's just g of x. There's no h in the g. There's no h in g of x. There's an h in here, but as h goes to 0, g of x plus h becomes g of x plus 0. And x plus 0 is, of course, just x. So look at this. Look at what falls out as a consequence of our seemingly interminable journey through algebra and calculus. G f prime minus f g prime over g squared. Put this guy in a lovely cloud. He has deserved it. We have proved that we get low d high minus high d low over low squared. That's what we proved. We have proven the rule of Adam Sandler, which again is the formal title. And this quotient rule, he's quite special. He's quite special. He allows us to prove some seemingly impossible things, or at the very least very unexpected. We can actually prove the remaining 4 trig functions, the ones in addition to just sine and cosine. So now that we know sine and cosine, we can rewrite all 4 of these trig functions in terms of sines and cosines. As we know from trig, tangent is sine over cosine. And at this point, I've rewritten tangent as a quotient. Prime time to use the quotient rule then. Stands to reason, low d high minus high d low over low squared. That numerator is cosine squared plus sine squared of the same thing. He's just 1, so I have 1 over cosine squared, 1 over cosine times 1 over cosine, which is secant times secant, which is secant squared. There's our derivative formula for tangent. Likewise, secant's 1 over cosine. I have rewritten secant as a quotient. Apply that quotient rule yet again. I get sine of x on the top, all over cosine of x times cosine of x, and I'm going to break that up into 2 fractions, 1 over cosine times sine over cosine. The former is secant, the latter is the definition of tangent, and we get secant times tangent. That is the definition of the derivative, or not the definition, that is the derivative of secant of x. So we've proved another formula. Let's prove a third one. We're on a roll here. Same deal, quotient rule that guy, and we get this, negative cosine over sine times sine, break it up into two fractions, 1 over sine. 1 over sine times the other fella, which is cotangent, of course, cosine over sine. And there is our formula for cosecant. The derivative of cosecant is negative cosecant cotangent. Finally, cotangent, rewrite him as a quotient yet again, and yet again we can apply the quotient rule, and yet again we're going to be able to use our trigonometric identities to rewrite that numerator. That's negative sine squared minus cosine squared, but if I factor out a minus 1, the inside of those parentheses is 1, so negative 1 is, well, negative 1. So there we have it. Negative 1 over sine squared, which is negative cosecant squared. 1 over sine times 1 over sine is cosecant squared, and put a negative sign, we get negative cosecant squared. All of that followed from knowing two things: the derivative formulas for sine and cosine, and the quotient rule. The quotient rule is really the big player in deriving those 4 trig formulas. So here they are. Definitely know these. Definitely know these from memory. But even if you don't know them from memory, as long as you remember the derivatives of sine and the derivatives of cosine, you can derive these on your own, just using the quotient rule and falling back on some familiar trigonometric formulas. So yeah, that's just what I'm emphasizing down below. Please memorize, but even if you forget, just know that you can derive them as long as you know the derivatives of sine and cosine and you know the quotient rule. And this is the power. This is why I took that time to prove the quotient rule in this video, because you can see the method. You can see the rationale behind what we are doing. You can see how it all links together in this grand mathematical tapestry. And here, let's add one more piece to that tapestry. We can now prove the power rule for negative whole numbers like negative 1, negative 3, negative 1,000,000. Because we've already proven the power rule using the binomial theorem for positive whole numbers. And in this video, we've proven the quotient rule. So we can actually use these two facts to now prove the power rule for any negative whole number. Let's see how that works. I'm going to let lowercase n stand for any positive whole number. And now consider the derivative. The derivative with respect to x of x to the negative n power. So x to the negative second, for example, to the negative 100, for example. That's what I'm doing right here when I say x to the negative n. Well, of course, I can rewrite that as 1 over x to the n, and now I have a quotient, which is prime time to use the quotient rule. Low d high minus high d low. By the way, d low we've proven in the first video, and x to the n minus 1, all over low squared, which I've shown there in gold. X to the n all to the second is x to the 2n using familiar exponent rules. First term of the numerator goes to 0. And now I'm left with this. I'm going to fall back on my subtraction rule for exponents. When I divide, I subtract the exponents if the bases are the same. So negative n times x to the negative n minus 1. So we are done. We just bring the negative n down and subtract 1 from negative n, and it works. We've proven the power rule for the other half of the whole numbers, the negative whole numbers. So more justification for the things we've been doing. And in a future video, we'll show it for all real numbers, but just to emphasize, this quotient rule, he's a very powerful guy. Very, very powerful guy. He gave us all the remaining trig functions, derivatives, and he's given us the other half of the power rule for whole numbers, for negative whole numbers. He's quite something, and that's why we waded through the long proofs for the product rule and the quotient rule, because they're very powerful things. The quotient rule in particular, he's quite something. He's quite something.